So I'm starting us off with finding the center mass of this body right here. So to start, to make this a little easier, all of these are uniform, which means they all have a constant density throughout. So I was able to put a point here and cause this point to be the place where I'm focusing. So the center of each of these is where the mass is acting, is what I'm using. So to start the equation, so first I'm going to draw my axis. So we have x direction, y direction, j hat, I. And then, so the equation I was using as seen on the board was the distance to the center of mass, which is written as this, is the sum of all the masses times the distance to where the origin is, divided by the mass of the whole system. So it's the mass times the distance to the origin, and all of those added up times the mass of the system. So for this one, it was really easy. It was just 4 kilograms d half minus and so this is for the bar on the left side. And now for the bar right above that is this is the equation for the bar just adjacent to the sphere. And then the sphere would just be 10 kilograms, however, it's at the origin, so its vector would be 0 in the I direction and 0 in the j direction. So we don't really care about that. But this would then be divided by the total mass, which is 20 kilograms, which in the end would give us the vector of negative 2.1 meters in the I direction and negative 0.18 meters in the j direction. So then finding the magnitude of that is just the square root of that. And that gives us the answer of 2.1077 meters.
So there's some best practices that Gracie has followed. I would like all of you to follow in more complex problems as well. For example, using the units for each of the quantities, all the vectors, the unit vectors she has mentioned appropriately, the brackets, so she's put the circular bracket inside the square bracket. Of course, for the entire numerator, you could put a different kind of a bracket, doesn't matter. So these are some of the things I'd like each and every one of you to follow. And of course, she started with the inertial frame of reference. Right now, for the calculation of the center of mass, it need not be an inertial frame of reference, but you need some frame of reference. It might as well be an inertial frame of reference, because the only purpose you're determining the center of mass is for the kinetics, in which Newton's second law will be applicable only if it's an inertial frame of reference. So done very well. Thank you.
Okay. So then for the next question, very similar, and again it's uniform, so the densities are the same. So I'll just write real quick. So the same equation, you said it's technically not in the inertial frame of reference?
No,
it is.
It is, yeah.
So this
it's not necessary for it to be inertial, but it's useful because when you go to the next step to beyond the center of mass or other things that you need to evaluate in kinetics, you will need it to be inertial. So you might as well start with it.
Okay. So we're just going to adjust this a little bit to incorporate the z-axis, or the, yeah. So this will be z, which is k hat. Still in the same frame of reference. So this is the axis we're going to be working with. So for this, I'm just going to go right beneath. And so I have the new reference would be 0.8 meters. And then it would be, so this is for the first bar, which is coming off of this right here. So we're finding from A. So this would be negative L I. In the X direction, this would be positive L divided by 2 in the K direction. So then from there we add the B bar, which is 2.4. And that's the mass, or the meters. And then that would be then multiplied by negative L half in the I direction. So then from there we move on to the C bar, which would be the 33 mass times, and that was negative L half in the K direction, K hat direction. And then we have one more, which was the D bar, which is the 30.6 for the mass. And then it has the negative L half, or let's see. So it's in the Y direction, so it's actually positive L half in the Y direction. And we have negative L in the K direction. So there's all of our mass times vectors. And then we're going to divide all of this again by the total mass, which we have as 8.8 m. So there's that. So this will give us a final vector. Final vector for our IISc is going to equal negative 0.204 in the I direction, plus 0.184 in the J direction, and then we have erase some of this.
How do you get the total mass to be 8.8 m?
So each of these has the mass times it.
Okay.
So I added them all together to get the total mass of 8.8.
Okay. So what do you get when you add them up?
Is it 9.8? I might have done it wrong. So you get this added together. Oh, it's 6. So that's 9.8.
Yeah.
Yes. So that's actually 9.8. So let me check here. See what I did.
Okay.
So it switches to
Right.
9 here.
Sure.
So I think I made that mistake and must have caught it halfway through.
Okay.
We'll see what's the unit vector off of this is. So yeah, so same unit vector for 80. I think I must not have corrected all of my notes. No. So this is actually what it is. So I made the mistake of taking a 1 off of each of these added together, and I left it but changed it here. So that was my mistake. So this would all be divided by the 9.8. And then the unit vector for this is just the square root of all these squared added together, which leaves us with 0.5526.
Units?
Units would be the mass, but it gives us mass in M.
But that cancels out, right?
Yes,
M
it
and the
doesn't give
numerator and
us a
denominator.
unit.
Yeah.
And then the L that we had before, is equal to
given
1.
to be 1. Okay, fine.
So that's how it cancels out.
That's
So yes.
I'll try to be on the side today. All right, so this is my problem. Ooh. All right. So this problem is pretty much, let's imagine it into two different parts, where one is the half sphere, another is the cylinder part, right? So we would just do what is given to us. Is there another marker? Yeah. Please, thank you. So what is given to us is length is 1.8 r, and r is equal to 1.3 meters. So we would just first see what is the volume of each one. So volume of cylinder would be rho v cylinder, which would be equal to rho pi r square L. Then volume of hemisphere is equal to rho v hem is equal to rho, would be equal to, yes, would be equal to rho 2 by 3 pi r cubed. So now we need to find where their center of mass is, which in this case for the cylinder would be at what length it is. So in this case it would be, for the cylinder it would be L by 2 away from its base, and for the hemisphere it would be 3r by 8. And then we just combine the center of masses, which would be.
So where is it 3r by 8 from? From what datum is it 3r by 8?
From its base, pretty
From
much.
its base.
Yeah. Sorry, I forgot to mention that. Yes. Whew. So it would be is equal to Cyn plus mass mass ATM and ZHEM, all divided by MCYM plus MHEM. Right, in this case, as I said above, Z of cylinder is L by 2 and Z of hemisphere is 3R by 8. So now we just plug these into the equations up here. So for the cylinder, it would be pi r squared is equal to pi times 1.3 squared times 1.8 times 1.3. So this would give us about 3.95 pi. 95 pi, and then we'll do the same for the hemisphere, where this
Units.
oh sorry no pi, just pi in this sense. I'll add the units afterwards. Do you want me to?
No, for each stage you need to.
So this would be
specify.
meters.
This is the volume. Volume is not in meters, right?
Oh, yes. Sorry. Then this would be meters cubed. My bad. I forgot to add that here. Then for the second one would be 2 by 3 pi r cubed is equal to 2 by 3 times pi times 1.3 cubed, which would come out to equal to 1.4646 pi meter cubed. Correct? And now we have to find their masses. So pretty much multiply this times rho times rho, pretty much. And then we need to find their center of mass. So for the center of mass of the cylinder, this would Z of Cyn would be equal to L by 2, which would be equal to 1.8 times 1.3 whole divided by 2 equal to 1.17 meters. And Z of hemisphere, ATM, it would be equal to L plus 3R by 8 equal to 1.8 times 1.3 would be 1.3 plus 3 times 1.3 by 8, which would get us a number of 2.8275 meters. That means 2.827 meters. Do you mind if I erase this?
Yeah, you can go ahead. But I would urge you, because you're talking about Z, you
Yes.
need to say where Z equal to 0 is. Though you have said in words, it's always good to draw your coordinate system and show where exactly Z is, the Z coordinate is.
From the
starting
base,
from.
yeah. Okay.
Yeah.
Do you want me to show it?
Yeah, can you just sketch the same thing, and maybe you could even do a 2D version of it.
So pretty much this is the 2D
Yeah,
version,
yeah.
and this is the base.
Correct, yeah. So you need
This
to
is
mark
where
the axis.
Z is from.
Yeah. Right.
I apologize.
Yeah, that's okay.
No, I thought it was already shown. That's why.
Yeah, that of course it's shown over there, but
All right, yeah. So now since we have all the numbers, all right, I'll just try to make it here. Now we have this formula ready. Just plug and chug in the numbers. So this would be equal to rho times 3.95 pi times 1.17 plus rho times 1.46 pi times 2.8 whole divided by rho times 3.95 pi plus rho times 1.46 pi. So this all the rows would get canceled, and our final answer, if we do the math, simple math here, would come down to be 1.6180 meters, which would be equal to about 1.6 2 meters. So this would be our answer.
Though they have asked only for the z component, what can you say about the other two components of the center of mass over here?
Like, what do you mean?
Typically, every point has 3 coordinates
Yes,
in a
yeah.
3-dimensional space.
Yeah, we would have to do the same thing for the other 2 coordinate systems.
Yeah, can you tell the answer without even doing that? Is it possible for this case?
I'm not sure. Like, how do you mean? Like, without looking at...
So, just like how you determine the z coordinate, you needed to go through this exercise, right? So,
Yes.
Some cases, as we have discussed in the class, it's possible to get to the location without having to do the calculations based on certain, I'm not giving you the word, but if you just recollect what it is.
Based on certain parameters? What do you mean?
No, it's essentially a geometric feature of this. What's so special about this geometry, either of a cylinder or a sphere or hemisphere?
It's round?
Yeah, so it's essentially axisymmetric.
Axisymmetric, yeah.
So if it's axisymmetric, what can you say about the x and the y? You don't need to calculate.
Wouldn't it be 0 in that sense?
Yeah, it depends. Again, you've shown only the z-axis. You have to if
Yeah.
you show all the 3 axes, x
Yeah,
and y.
like, yeah, so this is this would be like this, for example,
yeah.
right? Yes.
Yeah. So which would be x, which would be y?
In this case, that's the z. This would be y, and this would be x.
Is it a dextral triad now? Can you use your right hand thumb rule to see if I cross j is going to k?
I'm sorry, I don't.
See, when you say a dextral triad, it means a right-handed system. Right?
Correct.
So there are 2 systems, right-handed and left-handed.
Correct.
Okay? So we typically use as a convention the right-handed system.
Correct.
It's
Yeah,
not
right hand,
necessary,
yes.
but it's just that for consistency we
Correct.
use that. Okay?
Yeah.
So which means what it exactly means is that if you use your right hand with your
Yeah.
thumb
Yes.
and you cross from I to j,
Correct.
which is from
Going
the x-axis to the
y
y-axis,
correct.
you should get to the z-axis or
Correct.
z-axis, right?
Yeah.
Is it? Are you getting that here? Is the way you've drawn it?
Oh no, sorry, this is wrong. Then I see what you're saying now. Then it would be flipped in this case. Yes, this would be y and this would be x.
Right.
Yeah. Understood.
Yeah. So,
Yeah.
though for this simple problem, the way it is structured, all this is not necessary. When you go to more complex problems, all of this will make your life much simpler.
Yes,
Like you said,
absolutely.
you are going to calculate x and y. You wouldn't need to.
Correct.
Because now you'd recognize that axisymmetry.
Yeah. Correct.
So in some other problems, you may not have an axisymmetry, but you might have a plane of symmetry.
Yeah.
In which case, the center of mass would be on the plane of symmetry.
Absolutely. Yeah.
So you
Makes
only
sense.
need to find again one
Just one axis
which is
and then.
how far it is from the plane of symmetry.
Correct.
Okay. So
Yeah. Makes sense. Yeah, I wasn't
just
understanding.
being
Yeah.
precise and you will help you when you go to more complex problems because
Yes.
it's essentially a training to get towards more complex problems,
Yeah.
right?
I see.
Thanks.
The next one is also mine.
You had something similar to that, Nafis? You had something similar to this question in previous homework? No?
Units of stress or like what units of velocity modules units?
All right. So for this one, my question is which possible units of linear momentum? So what we need in finding momentum is we need 2 things: mass times velocity, pretty much. So it should be represented in mass. The units here one should represent the mass, and one should represent the velocity. So if we go first one, kg times mass by second by s. So here kg. So in this case, we can see that the product of mass would be kg, and the velocity would would be meters per second in the metric system. Yes, so the number 1 would be the possibility. So going to number 2, newtons times second. So in this case, what is the unit of newtons in the metric system? Let's look at it that way, so that it would make our problem be much easier. So 1 newton would be equal to 1 kg seconds. 1 kg times meters per second squared. This would
why is it so? Why is that true?
What's this?
Why is Newton kilogram per times meter per second?
Oh, so because it's in an area, velocity is like.
No, it's a fallout of Newton's second law.
Yeah,
which
F
says
equals
mass
ma.
into acceleration.
Yes,
So
correct.
Unit of mass is kilogram.
Kilogram and
unit of
yeah, exactly the
acceleration
same
is-
way.
So you need to say those things.
Oh, okay, sorry. Yeah. So, yeah, so applying Newton's second law here, where mass times acceleration, F equal to ma, that we know of, where mass would be in kilograms, and this would be, and meters per second squared would be its velocity, and we have another
Not velocity, acceleration.
acceleration, sorry. And here we have another s. So pretty much multiplying this by an s. So one s goes down. So this would be removed. So this would come up to be equal to kg times meters per second, which would also be correct.
Absolutely. Yeah.
So the third one.
So I just like to add some information over here. So remember in the very first class we talked about the impulse momentum equations, where you are integrating the Newton's second law with respect to time. So for that, this particular unit becomes a more natural unit, even though it's exactly same as kilogram meter per second, because you're integrating the force with respect to time. So it's force is Newton and time is second, and you end up with momentum, so which is what you see there. Whereas the original form of the Newton's law is in terms of acceleration, because it's rate of change of momentum.
Okay. All right. So now we go to the third one, which is slug times feet per second. So this would also be correct. This is just in a different metric system, where slug is used as the mass, and this feet per second is like meters per second used as momentum. So this would also be correct. And the last one, which is joules, J. If we break it down the same way by following the same concept of newtons per second, one joule would come out to be 1 kilogram times meter squared by second squared. This would not be a valid unit, because the mass can be because joules are units of work, if I put that correctly, right? They're units of work rather than which would not be used in linear momentum, pretty much.
So if it's the unit of work, how will it become kilogram times meter squared per second squared? So I want you to argue out what you wrote.
Okay.
So that's just mass times speed squared, right?
Correct.
So, but you said another thing which is also correct, which is joules is the unit of work.
Correct.
Right? So from the fact that joule is a unit of work, can you argue out that it is kilogram meter squared per second squared?
I'm sorry.
Whatever you have written.
Yes. So
how did you get to
same
that?
Same thing.
How?
F equal to ma. Do you mean that way, or how do you mean it?
Yeah, you can use whatever information you have.
So
but I want you to prove that yes, joules is kilogram times meters per second squared, rather than out of memory or just taking it from some source, right? Like what we did in the top when
Correct.
we did for Newton. We argued out using Newton's second
So
law.
second
that
law,
force
correct,
Times, force is mass times acceleration.
Correct.
So how do you get from work to kilogram meter squared per second squared?
So how should I explain this? I have it in my mind. I just don't know how to explain it, because it's been memorized in my mind pretty much. That one, like if you look at the Newton's second law, F equal to ma,
Okay.
right? for example,
But this has nothing to do with that, right? You're talking about
similarity
joules,
to
you're
that.
talking of work.
I'm trying to
Yeah.
bring similarity, right?
Okay.
If for example, if something is being worked upon, right?
Okay.
How can we calculate work on
Exactly.
it, right?
Exactly.
So that is what I'm trying to think of.
Right.
That imagine there's a block. This is 1 kilogram, right? How much am I moving, right? And how do I calculate how much am I moving? That's the amount of work that I'm putting it, right? That would be the amount of work that I'm doing.
Right.
It would be the unit of that would be meters squared, and how much second squared did I do it in, if that makes sense.
No, it
Does it-
doesn't.
Like, imagine if
So it's not about the mass, right? It's about the force that you're
correct,
applying.
yeah, that's what I'm trying to say. That
But you said mass, which is a 1 kg. 1 kg is a mass, not a force, right?
no. So
you are-
what I'm trying to say is, imagine if there's a 1 kilogram block here,
Mm-hmm.
right? So I have to if I want to move it, right? That's my work
Correct.
being in.
Correct.
How am I going to calculate that? That would be joules, right? So like if I'm putting in the force,
Yeah.
right? That is how it's going to move, if that makes sense.
Yeah. So what is the work? How is it defined in terms of force and the distance moved?
So like for example, this is I'm trying to move this, right? And the amount of force that I'm putting in
Yeah.
is how I'll define it. Does that make sense? I'm getting
Not yet.
He's asking you to derive this.
yeah, that's what I'm trying to say. In my mind, what
Derive it in the board. Derive it in the board. That's what he's doing.
No, you can explain it. You're saying work is related to force and displacement, right?
Correct, correct.
What is the relation between them?
force
Mathematically. Like for example, the relationship between force, mass and acceleration is mass times acceleration
Correct,
is equal to
correct,
force.
yeah.
Similarly, now you're saying that work, force and distance moved are related to each
Yes.
other. What is the relation between them?
acceleration in that sense. Like
No,
force
just
and
those
work.
three quantities.
Sorry, I'm getting confused
When-
here very much so.
So when I'm applying a certain force
Yes.
to move this and
Yes.
it's moved by a certain distance. So
It's force times
I measure the
displacement.
distance,
Yes.
I measure the force that I'm applying.
Correct.
How will I calculate the work that I've done?
It's the distance, displacement, which is the distance that
Yeah.
you covered times the force you put in.
Exactly. So you need to get to those units.
Yes.
So what is the unit of force?
Force is, why am I not getting this right now? Sorry, I'm getting blanked out. Unit of force, in this case, would be joules, right? Or like, how,
Unit of work is joule.
joules, yes.
Unit
Unit
of
of
force
force.
is
I'm forgetting this. Why is this happening? I'm sorry, I'm not getting it at the moment.
the unit of force is Newton.
Correct. Oh, okay, yeah. Sorry.
So-
why
so can-
I'm complicating it way too much. Then
Yeah.
So it would be newtons, right?
Yeah, Newton is the force. What is
Correct.
the work? You defined it correctly just a few seconds back.
Yes.
It's force times the displacement. You
Correct.
said, right?
Yes.
So what is the unit of force is Newton.
Correct.
What is the unit of displacement?
Displacement is in meters.
Yeah. So
So,
joule is Newton times meter.
meters. Yeah.
So then you write Newton in using
Oh.
Newton's second law.
I see. I
It's
see.
mass times acceleration.
Correct,
Kilogram
correct.
meter per second squared.
I see.
Then you multiply by another meter.
Yes.
Then you get to this.
Correct. Yeah.
Yeah.
I was complicating this way too much to the point where what I was thinking is what you were trying to ask is what is the force being applied on? That's what I was getting confused at. Does that make sense?
No,
Like,
here we are only talking about.
yeah,
units.
I understand. But
Right.
in this instance, when you were asking, I was complicating it too much. I understand what you're saying now.
Sure.
Yeah, but okay. I'm sorry. I just blanked out for a second.
Yeah.
This was too easy. Sorry.
Right.
Yeah. So in this case, joules would not be there. Yeah.
Because it has a meter per second extra additional
Correct.
to what
Not-
you
yeah.
require. Yeah.
Yes. Next one is also mine. Last one. Oof. All right, so I'm giving, consider particle A at mass given 6 kilograms, its velocity given v of A of 5i I hat plus 5j hat meters per second. calculate the magnitude of the linear momentum. All right, so frame of reference, first I'll draw that. So this would be our frame of reference, right? So we'll use the formula equal to MI, right? This would be the formula that we would use, and we are already given that MA is 6 kilograms. MA equal to 6 kilograms. VA is equal to 5 I hat plus 5 J hat meters per second. So we need to first calculate this, and then we can go calculate that. So this would be pretty much VA I hat is equal to 5 squared plus 5 squared is equal to square root of 25 plus 25, which would be equal to 5 root 50 equal to 5 root 2 meters per second. Correct? And then now that we have this, we just plug it into our previous formula, where this would be A equal to 6 kg times 5 root 2 meters per second, which would come down to 30 root 2 meters per second, which would be equal to 42. Oh, sorry, this is wrong. 30 root 2 kg meters per second. How can I make this mistake after? Okay, kg meters per second, which would come out to 42.43 kg times meters per second. Yes.
You need to put two vertical lines on either side of
Oh yes,
the
sorry.
momentum.
Yeah.
Because the magnitude. is
Correct. Sorry. Woohoo. Did the mic fall off?
No, it's there.
Wait. Sorry, the problem I solved is different from this problem. I don't know why.
Okay.
It looks the same, but they're different numbers.
This is the next one after this. You want for
Yeah, wait, this is off. It's homework 5, right?
Maybe we can do the one after. Did you solve the question that Toad just solved?
No, I didn't. I solved this one, but the numbers were different. I'm looking at homework 5, and oh shoot, I did the one. I did this one.
Assigned both of them.
Okay, yeah, but I didn't do this. I did this one, and this one, and this one.
those are the two ones that I did.
Okay, well, the numbering is off. Because I did 6, like the one labeled 6 in the homework.
It's
My
okay if it's
bad.
the same procedure and the numbers are different. You can give an attempt, and we will all try to help you out.
Alright.
Figure it out live.
Alrighty. Okay, this is linear momentum, so it's a bit different.
You maybe want to like do the ones you did, and then we can present, and then we can work on this one.
Sure.
Okay, that's fair.
Might be less.
Okay. Alright, I'll go with these two first then. So for this problem, we're given that a particle is moving on the x and y axis. So I'm going to first draw a coordinate plane. So that's z, x, y.
So it's not a dextral triad.
Huh?
It's not a dextral triad. It's not a right-handed system.
I don't get it.
The way you've drawn your x, y, and z, your right-hand thumb rule will not work. It will be a left-hand thumb rule.
Oh wait, is it going backwards?
No, it has to do with like the labeling of the axes. When you cross x and y, it should point in the direction. So if you do the right hand rule with x and y,
Right.
your thumb should point in.
Wait, is that x then?
Yeah.
Okay. Alright, so we're given that particle A is a mass of 10 kilograms and it's at 050, so it's right here. And then B is at 510, so right here. And they have their own respective velocities of -7i for B. So it's roughly, oh wait, no. It's like that. And then that one is 10, so like that. Okay.
So note that B is at 5, 10, not 10, 5, right? A is correct.
Ah.
Yeah.
Okay.
You
There.
use the erasers for chemicals on your fingers.
Okay. So we have to find the component of angular momentum about the z-axis. So it's going to be something either like that or like that, one of the two directions. We're going to find that as well. So the first steps that I took is to write out the formulas that we'll be using. So we'll need the vector formula of angular momentum, which I'm going to denote as h naught. And that equals r times, well, it's r times p, which is linear momentum, and then r is the radius about which it is rotating. But p equals mv. So that's the formula there. And we're also going to use the sum of angular momentum, which is sigma m naught dt equals integral of d h naught, which equals to h naught 2 plus h naught 1. And we're going to do the angular momentum calculation on both of these particles, add it up, and that will be the total angular momentum.
Yeah,
and also
it's
because
fine,
the
but
motion...
it's an overkill to use an integral here because you're talking of particles.
Yeah, I'm just doing
so you
like
don't
the
need
derivation so we
integration.
know where it's
so
coming
you have
from.
either the summation or the integration, not both, right?
Right.
So,
yeah, we're going to be using the summation because it's all in linear components. Or I mean,
But,
magnitude.
so what you're saying is true in reality, because in reality you don't have a particle. You will
Right.
have everything finite sized.
Right,
So you'll
yeah.
have to do an integration over each one of them and then sum over.
Mhm. Okay.
So, yeah, I guess I'll. Starting with particle A. So we know that for particle A, the mass is 10 kilograms. The velocity A is 10I, 10J, and then nothing in the K axis. And then the initial position is 5. No, it's 0, 5, 0. So then to find H naught A,
So the way you've written the units for M, can you write the units for the others as well? V, A,
yeah,
and P?
yeah. Okay. So to find H naught A, what we want to do is do the position, which relative to the origin, it would just be the position. So P would be equal to R. I'll just write that for reference. We want to do RA times MV. So I'm just going to go ahead and plug in the numbers since I wrote it up there. We want to do R times 10, which is a scalar. Oh, units. Which is a scalar, and then times the vector of velocity. And if we do that, we can simplify this, since this is a scalar times a vector, we can find the base momentum of 100, 100, 0, and then do the cross product to find angular momentum. I'm going to do a different color for that for clarity. So that is
Rather than X, Y, Z, I would suggest you have it as I hat, J hat, and K hat,
Yeah.
because essentially you're getting to a vector in those three directions.
okay. So if we first do that, like
And
do the
also,
cross
this
product
is a
there,
determinant, so we typically use vertical braces, not the flowered ones.
oh, like that?
Yeah.
Okay. So if we do the cross product, we get the H naught A is negative 500 K hat. Now if we do the same
Units?
thing, oh, right. Meters.
You have it right on the top, so you have meter, kilogram, and meter per second. So just yeah, perfect.
Yeah. And then if we do the same thing for H naught B, that would be, oh, I mean, I have to write down the variables again. So I'm just going to erase this and redo it for B. So MB is 4 kilograms. VB is negative 700 meters per second. And then position of B is, it is 5, 10, 0. So then we redo the calculation for H naught B. And then if we multiply that out, then we get RP, or R cross P equals negative 28.00 kilogram meters per second. And then if we multiply this out, do the cross product. Then we get 0, 0, positive 280. Okay, so then that would be a net 280 k hat kilogram meter squared per second. So using those two values, we can add that up and find the total angular momentum. So negative 500 So that is the answer to this problem. So on to the next problem. They ask us, consider the same two particles. After some time, the particles, if they have the same velocity, but they're at a different location, so the velocity is staying constant, will the angular momentum change? Now, we already know, just from memorization, that there is the law of conservation of momentum. So if there's no force acting on a particle that's in motion, then momentum will not change.
Which momentum?
Both. So if there's a force applied to an object, the linear momentum will change. If there's a torque applied, then angular momentum will change. And if neither is applied, nothing will change. So if we're given that the velocities are the same, then that means that there is no applied force or torque on the particles in question. So essentially, we know just by that principle that it will not change. But I did do a bit of math in order to prove it. So I think I will just leave the same variables for the sake of time. But we have our A and B, so I'm just gonna put A and B respectively. So then the masses, MA is 10, MB is 4. Should have done this in the beginning, but okay. 10, 10, and then VB. Oh. Okay. Okay. So I kind of took this as, okay, let's do something that's easy, multiply it by, after 1 second, let's see where each of the particles are, assume that the velocity is the same, and then recalculate the momentum and see if it changes. So it's a pretty simple test and doesn't result in too ugly numbers. So that's that's what we're gonna do. So I first found, I refound the new positions of A and B. So we know that, okay, I'm running out of boardroom here. I'm gonna put it up here. So we find final position equals initial position, or I'll just put P1, VT, and these two are vectors. All of them are vectors. Okay. So we can find for PA 050 meters plus velocity is 10, 0. And then times 1 would be the same thing. So we get a P final of A would be 10, 15, 0 after 1 second. And if I do the same thing for PB, then we would get
You also
the-
need the mass there, right? You're talking of momentum?
what?
Oh, this is position.
Yeah, I'm just
position.
I'm just
Okay,
finding
sorry,
the position
sorry,
after 1 second. So assuming velocity
Yeah, I
doesn't
got confused
change.
because the same notation for both the position P and translation. So, go ahead. Yeah.
Oh right, okay, my bad. I should have clarified it. I think I'll do R instead. Then that would probably make it easier. Okay. So yeah, so that's our final for A, and then for B it would be 5, 10 is the initial, and then the velocity is -7, 0, 0. So then the final position for that one would be -2, 10, 0. So finding that, we can kind of go through with the same process again, except instead for H0A, we would be using the initial position after 1 second, which would be 10, 15, 0. And then we still have to multiply by the mass times the velocity. So that would be like that. And here, this would change to 10 times 15 10 times 15, and then 100 times 100. And yeah, we just redo the same process. So there's nothing in I, nothing in J because K is 0, or the K hat values are 0. And then in the end we get 1,000 minus 1,500, which results in -500 K hat. So you can kind of see that for H0A, it still didn't change even though the position changed. And then we can do that for B as well. So that would be -2, 10, 0, and then -28, which is the mass times velocity. And here you can see it's nothing, nothing for I and J, and then -2 minus -280, so plus 280. So that also didn't change. So we end up with the same thing at the end. Angular momentum did not change.
Good job. Really appreciate you going beyond just the logic to
Yeah.
get
I also
a
did
second
have-
confirmation of that.
Yeah, and I also did have like a short application. So the law of conservation of momentum is really useful when we're looking at rocket propulsion, because for rockets, obviously there is a lot more that's changing, so momentum doesn't appear to be conserved. Momentum is conserved, but there's stuff lost as heat, lost as sound, and there's energy going in many different directions. But for the most part, what we see in rockets is that the thrust generated by the propulsor is downward, and we get to conserve that momentum going upward, and that's basically the governing principle of why rockets go up. It's because of the normal force and the conservation of momentum there. That's all really.
Change the slide.
Yeah. Thank you. All right, so for this example, we're looking to find the linear momentum of an F-16 that is doing a pull-up maneuver, and we're given the kinematics of the jet, and so as a function of the time, we can see here that we have our velocity, or rather, first I think it's more appropriate, we should start by defining the reference frame with which all of these kinematics equations are given with respect to. So we have the aircraft arcing upwards in that direction. So let's define our inertial reference frame, which in this case will be the perspective of the Earth. We'll have our x and our I hat, y and our j hat, and our, it's horrible, our z and our k hat pointing outwards. And this is the reference frame with which these velocity equations are given. Notation. And in this case, the first thing that I'm going to do is substitute in. We have our velocities in terms of the v naught, which is a function of t, and I want to write the velocity vector itself as a function of t to simplify things. So we can just for a second. We can write it as such. We also have cosine here, and then our angular displacement, or our phi, is given by another function of time, which has a constant, so we can write that. As well. All right, that looks right. And then, since these are both multiplied by the same, we need our unit vectors here. Show that this component is in the I hat direction, that is in the j hat direction. So then we have our expression for our velocity at a given time, and we also have the mass. It's another important given of the F-16, which is 15,000 kilograms, and we're looking for the linear momentum, which will denote as L at time equals 1. And so we know that the linear momentum as a vector is going to be equal to the vector velocity times the mass. And now we have expressions for all of these at a given time. And so we can solve for the linear momentum at time equals 1. We say linear momentum vector is equal to 2,000 kilograms times and then I think this for constant shall be units of meters per second squared. And then when we multiply this out, we get our linear momentum vector equal to this big number here. And this is all in units of linear momentum, as we talked about earlier. So it's going to be kilogram meters per second. And then the question asks us for the momentum, the magnitude of the momentum. So if we take the magnitude, pretty straightforward here. And we're also asked to report the momentum in 10 to the 6 kilogram meters per second squared. So we're going to multiply by 1 over 10 to the 6 to get 10 to the 6 kilogram meters per second squared. And then when we calculate this all out, we're going to get 3.84 10 to the 6 kilogram meters per second. That should be just meters per second, not meters per second squared. And I believe that is the answer.
Just for completeness, though in this case it's very simple that you have just a inertial frame and one single body, but typically you'll have more than one body, and also
Okay.
even when you have one body you will have many points on that body, because it's what is happening at one point may not be the same at some other point. So when you write the velocity and the angular momentum as v and l, not only do you need a pre-superscript but also a subscript.
Okay, so that would be the center of
Exactly.
mass, which is what
Exactly. Very good. Yeah.
the point that I'm finding.
Yeah. That's okay. That's fine. What about the L?
The L should,
No. See, angular momentum is about a point, but
yes.
the translational momentum is not about a point, but it's of a body. So if you call the aircraft as A, for example, then you'd say L subscript A.
Okay.
So you see the distinction between how we treat velocity and angular momentum. Translational momentum. Translational momentum is of the entire body, whereas velocity is of a particular point in that body. So which is why V has the subscript C, whereas L has the subscript A, which is the name of that body.
Okay. Thank you. Okay, and then now we're going to look at the next question. Just the same situation, but this time we're going to be looking for the magnitude of the angular momentum about the center of mass, and we're given the pitch moment of inertia about the center of mass. So these are the important quantities here. Right at the givens. 275,000 kilogram meters squared. And then because we're looking for the angular momentum, we also want to know the angular speed. Because this problem that we're looking at is given as just two-dimensional motion with our single rotation about only the k-hat direction, we can look at this as a scalar problem. So we can say that our angular momentum about the center of mass in our inertial reference frame I is equal to the angular speed respect to I times the mass moment of inertia about the point that we want to find the angular momentum. And we do know that omega z is just a given. So if we just plug in these two numbers, ends up being a pretty simple calculation. This is the magnitude and this time it's also asking us to do the same unit conversion, so we're just going to write that out. And then when we do this calculation, we end up at 0.0825 10 to the 6th kilogram meter squared per second. I believe is also the answer we're looking for.
I just want to put an underline or a vector symbol over h. So even though you're
Okay.
talking about magnitude, within that it's essentially a vector. Yeah.
So if would it be appropriate to write this without the magnitude
Absolutely.
brackets like this?
Yeah.
But when you put them on,
Absolutely,
you
yeah.
need okay.
Because that's how you're defining that notation, so it's okay.
That makes sense.
Absolutely.
Thank you.
Can you change the slide? Yeah.
Oh, yes. Or- oh,
Oh, it's already.
yeah, it's like the same
Looks
format.
very- yeah. Because what is asked for is different.
All right, so first I begin by defining a coordinate plane. And this is like 2D motion because the velocity is given in I and j. So I'll give x and y in I hat and j hat. And then, let's see, it's an inertial reference frame. And so first we know that the sum of all forces is equal to mass times acceleration. And then so this is asking for the sum of all forces. So basically my approach here is we're given a mass, and so I'm trying to find this acceleration vector. And so first I'll start by writing out some givens, which will be important later. So our V naught is 273 minus 5t. And then, let's see, our WZ, or sorry, omega z is 0.1 radians per second. And then our mass is 15,000 kilograms. So we are given a function that defines velocity. So that would be velocity equals, and I guess I'll write out the full equation first, just for clarity. So you have v naught of t. Oh, this is a function of time. Cosine, and then theta of t. So this is also a function of time. The I hat direction plus v naught of t sine theta t in the j hat direction, and
So this is the velocity of the center of mass of the
oh
airplane.
yes. Okay. There you go. And I guess I should write c there as well. Okay. And then so we have this v naught, which is given here, and we're asked for. We also have the omega. Let's see, where is it given? Omega z t is theta, and so we can replace omega z with theta t, and then we can replace v naught of t with the given equation. So that'll be And then this will be all in meters per second since it's the velocity. And then, so now we want to find the derivative of velocity to get the acceleration. And so this is a product rule where we take the derivative of the first, multiply it by the second, and then we add it to the first times the derivative of the second. Wait, did I already say that? No. Okay, sorry. Derivative of the first times the second, and then the first times the derivative of the second. And we do that for both the I and the j component. And I'll kind of just, for the sake of time, write it out quickly. One relevant comment is this WZ I'm treating as a constant here because it is defined as 0.1 radians per second. So when I take the derivative or do the chain rule for the trig functions, I'm doing the derivative of the inside is just WZ because it's WZ times
Omega.
T. Oh, so omega, sorry. And that is all in meters per second squared. Okay. And then so if you plug in the time t equals 2 seconds, because that's given, into the t's in the function, and then you plug in actually, I think, oh yeah, and then you plug in for omega z 0.1 radians per second, you get negative 10.125 in the I hat direction, plus 24.782 in the j hat direction, in meters per second squared. And then, so now we want to find the force. So we use this equation from before. We substitute this mass, which is 15,000 kilograms. And then we have this, this equation. And I guess maybe I should write A since it's a force on the body A. Equals. Okay, and that multiplication of the mass times acceleration comes out to be negative 151,875 in the I hat direction, and I'll put a unit after, and then 371,730 in the j hat direction in newtons. And now it's asking for the magnitude, so we have to do the square root of the squares of the I and j hat components. And that comes out to be a big number, 401,558.474 newtons. But then, so for the very last step, it asks us to give it in 10 to the 6 newtons. So we can simplify this to be, if we round, 0.4016 times 10 to the 6 newtons. And that is my final answer.
Good to see everything being precise in terms of all the notations. Good job, Andrew.
Okay, thank you. And then this next question is a little bit more simple. Okay, so it's asking for the sum of all the pitching moments, and then so we have this equation that the sum of the moments about the center of mass is the time derivative of, and then since this is 2D, we have a more complex equation, but with 2D we can do a simplification. So it's the time derivative of the moment of inertia around the center of mass in the z, and then we have that multiplied by omega z in the k hat direction. And then so we're making the assumption that the mass is constant, and this is because like we can just assume that it's like the short flight time, the fuel is not like significantly changing the mass of the plane. So we can take out this this moment of inertia, and then so now we have this equation omega z. So now we have to find the time derivative of omega z, but if we look, omega z is given at 0.3 radians per second, which means the change in time is 0. So then the total, it'll be a coefficient times 0, so that would end in 0. And so like the sum of all moments would be 0. And I think this is not a function of time, it's a constant that you multiply, which is why you take it out. I might have said that incorrectly before.
No, you're right. What you said earlier was right, because see, when the mass changes, your I will also change, because the I is defined with respect to the mass distribution.
The reason I said what I just said was I got a little bit confused where, so my logic for omega z, well, I said that this doesn't change in time, so it comes out to 0, but I said that this doesn't change in time as well. I guess it's 0 times 0, but if this had been a function of time, would it still be 0 since this changes 0?
Yeah, as you said, the duration that we are considering is very short, so the fuel burn is very less. The mass change is very less. And since the distribution of mass is what contributes to your IZZ calculation, its change is there, but it's too small. It's negligible, and therefore it's approximately 0 times approximately 0.
I see. Okay, thank you. That makes sense.
Microphone.
So it's gonna be fun. So we're working in English units this time. We're seeing that we're given 2 bars, both weigh 3.1 pounds per foot. There's like a weight distribution across the bar, and we're given the length of each bar as 4 feet for the bar A and 6.3 for bar B. So we're also given a reference frame or coordinate system, and it actually works well because it keeps everything in positives, so you don't have to work with any negatives. So y, j, x, I. And we'll have the origin located where the bars intersect, so in that bottom right corner. And so based on this, what we can do is first convert the distributions that we're given, the weight, into actual masses so we can find where the center of mass is. So in order to do that, we have to know what the gravitational constant is in English units, and it's going to be about 32.174. We're using English units, so it's going to be feet per second squared. So using the two components that we're given, so for bar A, we'll say, we'll find mass of A is going to be equal to, we're going to take the distribution, so 3.1 pounds per feet, multiplied by the length of the bar. So for bar A, it's 4 feet. 4 feet. And then since we're given a weight, in order to get mass, we just divide by gravity. So I'll just put 32.174 feet per second squared. So based on this, what we get is a final answer of 0.385. If we look at the units, that's going to be pounds, pounds times second squared divided by feet, which is the same thing as a slug, which is the unit, the English unit for mass. And so we do the same thing for bar B, where we have basically the same distribution of gravity, or of weight, where it's 3.1 pounds per foot. The length is different in this case. So for B, it's going to be 6.3 feet. I put it on the wrong side. 1/6.3 feet. And we're dividing by gravity again to get mass. And in slugs, this is going to end up being 0.607 slugs. Okay, so now that we have the mass, we can move on to actually finding where the center of mass is going to be for the overall system. So in order to do that, what we're going to do is we're going to sum. First, I split up into two different components because the bars are actually on specific axes, so we can actually specifically describe where they are. So for the x component, we'll say as the I hat component. The center of mass is going to be our sum of the x coordinates of whatever component that we're looking at times its mass over the sum of all the x's, or sum of all the masses. And so since these are rods, we know that the corresponding center of mass for each relative bar is going to be at half its length. So for example, for bar B, the center of mass will be at the half point, which is the only variable that's really on the x axis. And then for the bar A, it'll be half of its length, and that'll be only in the y component. So if we're doing the x component, it's just going to be the x coordinate of where the center of mass for B is, so about half of 6.3. So 6.3 feet divided by 2 times its mass, which we just calculated to be 0.607 slugs, over the total mass, which in this case is going to be where we add them together. So it's going to be 0.385 slugs plus 0.607 slugs. Basically what this indicates is that, I guess I'm not including it, but the x component for bar B would just be 0. That's what it's really showing. And so we find that the x coordinate for where the center of mass is going to end up being 1.93 feet. If we do a similar thing in the j component, we'll see the sum of the y times mass over the sum of the total mass is going to be the same on the denominator as 3.85 plus 0.607 slugs. But this time, since we're talking about y, we'll see that bar B has 0, and we're adding the y part component from bar A, which is going to be its length divided by 2, so 4 divided by 2, times its mass, which we calculated as 0.385. Times 0.385 slugs. So that comes out to a final answer of 0.77 feet. So now we know where the center of mass is, so it's going to be somewhere around in between the two bars. So what we can do to find this is use the parallel axis theorem. So we'll find the moment of inertia for each bar around their center of mass, and then add their distance to the center of mass to find the final answer. So I included a screenshot from the textbook where it gives us the formula for the center of mass for a rod. And we'll see that it's m times, I guess, length squared divided by 12. So let's do this for both bars. And so we'll say this is the inertial reference frame. And then if I wanted to draw a bar, I would say this is bar A. This is bar B. So if we're doing so bar, the Z direction, inertial reference frame for bar A is going to be 1/12 times its mass. Its mass was 0.385 slugs times R, or the length for A, which we said was 4 feet. 4 feet squared. So this ends up being, I guess I'll just do them both first. So and then for the B, it's going to be 1/12 mass of bar B, which is 0.607. And then 6.3 feet as its length, squared.
These moments of inertia are independent of the frame of reference, so you don't need a P superscript value for that.
I didn't need I, right? That was it? I didn't need to include the
that's
superscript.
fine. Yeah, but it's the same in any frame of reference.
Okay.
It's just based on the mass distribution.
Okay, based on this, and then we add for each component the md squared. We're doing the parallel axis theorem, so the mass is going to be the same. So 0.385. We define what the distance is. In order to find the distance, we'll say d1 is for A. We just use the we just use the distance formula. So square root for body A. We know that the x component was 0 for body A because it's vertically along the axis, the y-axis. So it's 0 minus, well, I guess we can say, we can say plus because the axis is flipping this way. So 0 plus what we said our x component was, so 1.93 squared plus the other component, which is our y component, which is 2, because it's just 4 over 2. So it's 4 divided by 2, half of where the bar is. That's the center of mass for the bar A, minus 0.777 squared. And what we get for this is about 2.28 meters. So you can put this right here, 2.28 meters. That gets squared. And so for bar A, the moment of inertia is going to be 2.52 slugs per feet squared. And we can do the same thing for bar B, where this time our distance is going to be, we have an x component this time. So it's 6.3 divided by 2 minus our x component of 1.93 squared plus, we have 0 for where the center of mass is for B along the y. So it's going to be 0 minus, or 0 plus actually, 0.777 squared. I guess either way it ends up being the same. So you had 1.45, should have been feet. Feet. 1.45 feet for the distance between the center of mass of B to where the center of mass of the entire system is. And so we can put this in here. So it's going to be 0.607 slugs times that 1.45 squared. So we get a final number of about 3.28 slugs per feet squared. And if we sum those together, we get our final answer of 5.8036 slugs per feet squared. And that's our final answer for what the moment of inertia is around the center of mass. Okay. The next question we're doing a similar sort of thing, except in this case, the geometry is different. So we're no longer working with just bars. Now we have an additional semicircle below it, as well as the top rod is just going to be the same sort of rod equation as before. Except now, instead of asking it about the center of mass, I think they're asking it for around the origin O, which is at the very tip of the rod. So I'm going to redraw the coordinate system just so it works better for this equation, for this system. So this is still 2D, so I'll keep it as 2D. So now we have, I think it's better if we have the Y pointing downwards and the X pointing this way. Y, J hat, I hat. And then our origin is here. And so if we just draw out the rod goes down, and then below it is this half semicircle. So with the rod, we know the same thing applies, where the center of mass is going to be about the center, or halfway around the length. So since we're looking for the moment of inertia about point O, the equation where we said IR, say I, R, ZZ of the rod would have been 1/12 times mass times length squared. But if we're specifically looking for this, at the point of origin, we would do the parallel axis theorem. So you would add mass times length divided by 2, because that's the distance from our center of mass to where we want the moment of inertia squared. And we find that this adds up to about 1/3 mass times length squared. Because when you square this, it becomes L over 4. And so 1/12 plus 1/4 equals 1/3. Okay, and then apart from that, we want to do, we can plug in numbers for this right now. So for IZZR, for the rod, it's going to be 1/3 times our mass. We're actually given mass this time, and it's in metric units. So for the rod, it's 0.6 kilograms. And our length we were given as, for the rod, as about 1.3 meters squared. And so I believe this ends up being 0.338 kilograms meter squared. So next up, we're looking for the semicircle. So for the semicircle, what I found is that the equation given, as we've shown in this table that I got from the textbook, for a semicircle, the moment of inertia equation is actually given as 1/2 mr squared. Now the interesting thing about this equation is that it's the same as if it was a solid circle. It would still be 1/2 mr squared. The only difference is that the mass is in half. And also the center of mass is different when you compare a semicircle as opposed to an overall circle. Whereas if we imagine this to be like an overall circle, we would know that obviously since it's symmetrical, the center of mass would be about this point. But since we're given half of the circle, so this mass isn't really here, the center of mass actually ends up being somewhere within where the circle is. So it's below that point. And so I added a picture, a graph or a chart that I got from statics about where to find the center of mass. We can see for the center of mass here, the equation would be 4 times the radius divided by 3 pi. And so when we're using this equation, 1/2 mr squared, we have to add in an additional term to basically describe this change in position, much like how we use parallel axis theorem. And so instead of doing 1/2 mr squared, we would do 1/2 mr squared, and we would subtract parallel axis theorem. So we would do 1/2 m, and then I think our length here would be where the center of mass should have been. So 4r over 3 pi squared. And so what that would do, it would get us from this position, where we currently are, to down below to where the center of mass actually is for a semicircle. But we're obviously looking for the moment of inertia about point O, so we'd add another term where we'd have mass times this total distance from the point that we traveled and then all the way to the origin. The origin, we know, is going to be all the way the length of L. And this additional term, which we just added, is 4r over 3 pi. So it would be L plus 4r over 3 pi. And since we're given all these numbers, we can plug them right in. So 1/2, the mass is about 2.5 kilograms for the semicircle, or for the disk. The radius is 0.15 meters. Square that, minus 2.5 kilograms times 4.15 meters over 3 pi. Plus mass again, so 2.5 kilograms. Length of 1.3 meters plus 4.15 meters for 3 pi. And so when we add this all together, we get a final answer of 4.667, and it would be kilograms per meter squared. And since we found both components of IZZD, we found both of the disk, the semicircular disk, and of the rod. In order to find the overall moment of inertia, we would just add them together. And so our final answer for the system ends up being about 5.004 kilograms meters squared.
Okay, so I have the next two problems, and the second one I found a little bit difficult, so I would appreciate some help on that one. But this is the first part. So we're given a cylinder, and we know some values about it. We want to find the location of the new center of mass after a hole is drilled through the cylinder. So I'm just going to replicate this image and then define our coordinate axes and frame of reference. So we have a hole here. It has some radius little r. We have a point Q, which is the geometric center of this cross section of the cylinder, and it has radius big R. And then we have our new mass center, point C, which is above Q, due to the result of drilling this hole. And we know the distance between the radius of the hole and the geometric radius and the geometric center here as D, and we want to find this distance, which I'll call L. And for our frame of reference, we can say that these are our axes and here's our body. Okay, so what we need to find is essentially the center of mass. So we know that this is going to be like a center of mass problem, and we have an expression for that. We know that the center of mass would be equal to the sum of the masses times the distances from the center of mass over the, I guess, the thing. The question is now, how do we find sort of the masses things? And the way I thought about this, which I'm not sure is completely correct, but I thought of it as we have the mass of the cylinder, and then we have the mass of the hole. So the mass that's remaining, rather the total mass, would just be the mass of the cylinder minus the mass of the hole. But there's a lot that we don't know. We won't be able to actually find the masses themselves because I guess the way I kind of thought about this was the fact that it's a cylinder means that it's a rigid body. And we know that the mass of a rigid body is equal to the integral of its density with with respect to the volume. Because we don't know the length, we don't know the, like, I guess, if we were to say our z-axis is sort of protruding out and the length of the cylinder would be going in that direction, we don't really know that value. It's not like it would really matter because it would cancel out. But even so, if we were to look at it just in 2 dimensions, another integral for that would be like the 2-dimensional density with respect to the area. I don't really know what that's called. I don't know what it's called if there's like a mass on a 2D.
Yeah, it's mass per unit area. It's essentially
Okay.
areal density.
Okay. But we also don't know this. But that's okay because it'll all cancel out. I'm just gonna keep it. I'm just gonna put this symbol here because it was a little less confusing when I did it that way. But towards the end, it'll all cancel out, so it'll be fine. So now we can find expressions for the mass of the whole cylinder without the hole, and then the mass of this little hole that's there, which would be equivalent to, if we're treating this as being constant density, that's what I'm assuming here, because we don't really know much else about it, then this would be a constant. This could come out of the integral. So then the integral of dA would just be a, and we know that the area of a circle is going to be pi r squared. So for the bigger circle, we would get pi times big R squared, and for the little hole, we would get, assuming it is a constant density, we would know that the sort of density in this little thing would be the same as everywhere else. So the sigmas would be the same, and we would know that the radius is little r, so that would be the mass of the hole. So then the mass of the remaining area would be equal to just the subtraction of these two. So I can sort of factor out the pi and the sigma and the pi, so then we get this expression. And that's what would be going in our denominator. Now we need to know what would go up here. And it's essentially sort of the same principle. So if I just write down here, then we're just finding the product of the mass and the position vector for these two things. But we're finding the magnitude as well, so we can probably just use the scalar values and we'll be okay. So with that, we know that what this will sort of come out to be is okay, I guess I'm a little confused about how to represent this symbolically, because I was able to do it, but okay. So I'm confused about how to represent the numerator like symbolically. So if I were to think about like what the top actually means, I think that's part of where I was getting confused while doing this problem. We would be trying to find the distance. Well, we're solving for L, but from okay, wait, I have a question. How I'm confused about how, like, in general, when using this equation, if you're trying to find the center for the top term, at least, how do you factor in like sort of the difference between because I guess it's weird because when I try to think about like how to use the formula, I think I'm confusing like the geometric center with like the mass center, and that's what's throwing me off because when I'm trying to visualize it, it's like I keep thinking that this point is supposed to be represented like sort of the difference between these two in the top, but we don't know that. Am I supposed to be trying to treat this as the center and then take these distances?
No, see, the question is where is the center of mass?
Yeah.
So
yeah.
the drilled cylinder.
Mm-hmm.
So now, whether it's the numerator or the denominator of that term that you have written RC,
Yeah.
essentially they are sums, okay? Summations.
Yeah.
Right? So summations can involve positive and negative terms. So just like in the denominator you had a negative term, so rather than calling it mass of the whole, it's essentially the mass of the material which is removed
Right.
during the drilling, right?
Uh-huh.
So it's not the mass of the whole. Mass of the whole is 0.
Right.
So it's the mass of the material that you have removed. So which you rightly put a negative sign for,
Yeah.
right? So when you wrote that last equation there, m remaining, you have written a minus r squared there, which
Yes.
is right. Okay. So same logic holds for the numerator as well. So essentially, the original mass center was at the geometric center.
Right.
Now it's
Yes.
moving away.
So
And,
right.
and there's no difference even if you had not been asked for mass center but the centroid,
Yeah.
which is a geometric center,
Mhm.
you would get the exact same result. So don't get confused with the fact that it's a center of mass.
Okay.
Same logic holds.
So just to clarify, the difference there would be between finding the centroid would be that the mass term would be, instead of using mass, we would be using, is it area? For the,
Come again?
for,
Come again?
if we were to be solving for the centroid,
Yeah.
I know it's a little bit unrelated,
Yeah,
but I
yeah,
just,
yeah,
to parallel the concepts,
yeah.
would instead of using it by mass, we would be using it by
Areas.
areas.
Yeah.
Okay. So
So essentially, because it's a uniform density,
Right.
whether it's the area or because you're rightly using that sigma, right?
Uh-huh.
That areal density is a constant, just
Right.
like the material density rho is a constant because the length is a constant.
Okay.
Unless, of course, the hole has been drilled only partially through the cylinder. This is through the length of the cylinder, and therefore you will have a constant rho and sigma,
okay.
right?
So then, in this case, so to my understanding, there's supposed to be a subtraction here, I'm pretty sure,
Yeah.
but my confusion is about the first term, where the first term would be the mass center without the hole, correct? Okay.
Yeah.
So that would be I guess, the mass of the cylinder times big R, and then minus the mass of the hole times little r?
No, it depends on where you're drawing your coordinate system from, right? So where is your origin?
Okay. I guess. Oh, okay. I guess yeah. It's easier if it's in the center. Then that better.
Exactly. Yeah. So what would that be?
So then this would be a 0.
Exactly. Yeah.
And then this distance would be d then, right? Because this distance for this r would be d. Okay. Okay, yeah, that makes more sense. So then this term would cancel out, and we have and little r we know is 4.5 meters times, well, wait, this is actually, it's negative. But we are finding the magnitudes. Let me just make this as well. Times 9.5 meters over 25.3 meters minus 4. Oops, I'm sorry. And I think that should get the answer, which is 0.3104 meters. Okay, so I guess I have one question.
Yeah.
How does this, like, I think I'm confused about the geometry of it a little bit still, because it's essentially, so without the hole, we've found the center of mass. And because we set our coordinate system to be here, then the distance from, like, for the r term, it would be 0 because we haven't moved from the.
Yeah.
Okay. Okay, I think I understand.
No, so if you, instead of a hole, if you think that you're actually adding a mass over there, okay? So then you would see the same logic holds with a negative sign.
Okay.
You see? So if there was an
Yeah.
addition of mass over
Right.
there, then you would have this center of mass moving towards it.
Right.
Now you're drilling a hole and removing the material, so the center of mass is moving away from the hole,
Okay. Right.
because more of the mass is on the top rather than on the bottom, which is why it's moving up. Okay?
Okay.
And it doesn't matter where the hole is, because you will always tilt your axis x and y such that it's the y-axis is along the line joining the two centers.
Okay.
Okay, so here it's shown almost, it's like a vertical thing, right? The hole could be anywhere.
Yeah.
Doesn't matter, as long as it's at the same distance. I can introduce my x and y axis in that direction to align one of the axes with the line joining those two centers.
Okay. I see. Okay. So that's the first problem.
Okay.
Then the second one is just that we need to now find the radius of gyration about the new mass center, and it's using slightly different numbers, but okay, so we're gonna need to use this expression again to find this distance. So I'm just gonna do that again. Okay. So now we need to find the radius of gyration. And so to do that, we know that we have the expression for it where k squared of c is equal to the mass times times the wait, no, that's not right. Hang on. Mass times k squared c is equal to the moment of inertia. And so we essentially need to solve for, actually, maybe, so it's like that since we're looking at the moment of inertia about the z-axis, we need to find this term. And the way we can do that, I think, is we can sort of say that this is equal to the, well, c with respect to the cylinder plus with respect to the hole. I was also pretty confused on this as well, so I'm not totally sure how to like kind of go about it, because I wasn't able to get to the correct answer here. So, but this is, so I'm kind of just doing it live because I got really confused. But okay, so this, now to find both of these terms, what I think you do is that this would be equal to of the cylinder about point Q, which is the geometric center. Plus L squared.
You're right.
Okay.
That's the first term.
Right. And then this would be equal to
you would want to introduce another point over there, just like you have C and Q. Q is the center of the
okay,
this
one?
You can call it, yeah. You can give it a name. You can call that point something.
Maybe I'll call it point P.
Yeah.
So
now you want to get to the, again, it's not the moment of inertia of the whole, but of the material which is removed from
right,
the whole, right?
yes,
So,
yes.
So that you can get about P first, and then you can use the parallel axis theorem to go to Q, just
So
like how you did.
would this term would be
See, what
P
you need is
or
about Q, right? For in
about
both the
Q,
cases.
yes.
So about C. So
About
the first one you got it about Q. Now the second one you get it about P, and then add that. Right?
Okay, I see.
Because you have to get it about its
Right.
center of mass. So for whatever material was removed from where the hole is now, its center of mass was at P.
Okay.
Right? So then you are adding the mass of that, not the disk, but of that whatever material you removed. So it's not the same M.
So this would a
In
different.
your notation, it would be M whole.
Oh, okay, right.
No.
Or
there it's
well,
fine.
there it's
There
fine.
it's fine,
Okay,
yeah.
okay. Okay.
So now, what is the distance that you have is D plus L. Yeah, correct.
Yeah. Okay. So.
You understood the logic, right? Or you're still confused about
I think
anything?
I understand it.
Okay.
I think my confusion is with the like. I think that we're adding a removed mass, essentially. I think, like, so we have this new center P for this area, and we're finding the moment of inertia of that, but would that not be subtracted, like from the, or rather, would it be, I'm confused at what this term represents, I think, because I know I have to use it, but I don't know what it represents.
The confusion is because you're calling it a hole. It's essentially that material you're removing from the hole, right? From where the hole now is, right?
Okay.
So the original cylinder was intact. So you're removing some material from the hole. So essentially, you can think of it as a separate problem where you want to get for the intact cylinder as a combination of this, what you have now, and the whatever was the material which was removed. Let's say we are just scooping it out, so that just another smaller cylinder has come out of it, right?
Okay.
But it's just that it's not located at the same center. The axes are not coinciding. The axes are at a distance d from each other, right?
Right.
So now you can see the logic of adding these two, of the actual drilled one and the removed material. They should contribute towards the overall thing. So all that you're doing is to take that sum. In that sum, you're taking one of the terms to the left-hand side to make it negative.
Right.
Okay. So the logic which you already used in getting the mass, the m remaining,
Yes.
is the m cylinder minus the m material removed.
Right. Yes.
The same logic holds for your I as well,
Okay.
because it's about the same point. If it was at about different points, then you can't do that. But remember, you're taking both with respect to C,
Yes.
right? So you can add or subtract them depending upon whether the two bodies are joined or one is removed from the other,
Okay.
respectively.
Okay. I think I understand that better now. So I guess my follow-up question to that is whether or not this term is being added or subtracted. Is it because, well, because I mean, in the logic here, I remove mass from the overall cylinder. Here, is that the same thing here?
Yeah, see, just think of it this way, right? So essentially, you're looking at, think of this as the intact cylinder. Everything is there in it, okay?
Yeah.
It's not, no hole is drilled. Now I can think of this as made out of two parts. One is the same thing with the drilled hole, which means that
Yes.
the material is only over here, plus another small cylinder over here in which was just scooped out of it, right?
Okay.
So now
Yes.
all that you're doing is to take this to the left-hand
Oh, okay.
side
I
and make it
understand.
negative, right?
Okay. Yes.
Which is exactly the same logic you use there, just because it's a new concept, you're thinking it's different, but the same logic holds here as well.
Okay. Okay.
And that holds because both of these are C. If one of them was different, then you can't use this logic.
Okay. Thank you. Okay. So, in that case, we can then find each of these terms. So, the moment of inertia for a cylinder, the expression for it is 1/2 mr squared. We had solved for the m's over there, so I'm going to just keep that notation. Plus Okay. So my two expressions. And we can combine them to get well, I don't know, maybe I shouldn't combine them yet, but okay. So then so the moment of inertia about C would be equivalent to okay, I guess, so my question is, like, I understand the, like, the concept here, but I guess I'm confused at what I solve for. Is this first term representative of the full cylinder without any hole, or?
No, what you want to get to is that, right?
This is what we want to get to.
You want to get to. So this is this logic you understand because this is a set of two actual materials making up one bigger one. Okay.
Yes.
So now you are all that you're doing is that plus smaller circle cylinder. You're moving to the left hand side to get to what your real body is now. The question that's being asked for.
Okay, so I think maybe it's my notation that is confusing me. This is the full, or this is what I thought I was trying to solve for, and I was thinking this would be the full. So in that case, would I not be subtracting?
Yes.
Okay. Okay, that's what okay.
Yeah.
Makes more sense. Okay, so, right, then I'd be subtracting these two expressions. So I'll just write that here. That'll be equal to okay, right. So that's the expression. And now that we have that, we can put this back into here. So let's isolate the radius of gyration. Let's do that and put in this equation, this expression. So I'm going to put the mass first. The mass first would be the mass that's remaining, which was this expression that we found here.
Yeah.
So I'd put that at the bottom, and I would put this big thing at the top. I don't really have the room for it, but know that these two terms would cancel out, so it ends up not being really needed. And then we can simplify this expression by plugging in these known things and taking the square root. I'm not gonna write it here, but, or unless I should. Should I?
It's okay.
How much? What time is it?
It's okay. I think it's 1:20.
Oh, okay. I don't. Okay, so maybe I won't.
You understood the logic, right?
Yeah.
So that's good.
Okay. I'm sorry.
No problem.